In Chapter 4, Section 1, we are looking at graphing relationships, and we have three key words here. If you have a graph and it says increasing, that means the graph is going up. If you have a graph and it's decreasing, the graph is going down. And if there's something that's a constant, that means your graph is horizontal. So our first two examples, we need to figure out which graph matches this. And the first one says, each day several leaves fall from a tree. One day a gust of wind blows off many leaves. Eventually there are no more leaves on the tree. Which graph best represents that? So first of all, we have several leaves falling, which is the first thing. And we have a huge gust of wind, where we would have a bunch of them fall. And then the third thing is they continue to fall at a slower rate. So this one matches up with graph B. This is several leaves falling. This is the huge gust where it drops very sharp, and then they each fall, and eventually there are no more leaves on the tree. This would show an increase of leaves, like in the spring when the leaves go on, and then this would be through the summer, and then this would be in the fall. And this one would be leaves falling off a tree, like a huge gust of wind, and then no wind for a while, and then another gust that blows the rest of them off. Number 2, the air temperature increased steadily for several hours. So it increased steadily, went up. So this is the first thing, it goes up. Then it remains constant, which will be flat. At the end of the day, it increased slightly, so it went up. And then the fourth thing that happens is it drops sharply. So our graph needs to go up, remain constant, up, and then down. And that's going to match up with graph C. 3 through 5, we need to match these three graphs with these three stories. Number 3, a tomato plant grows taller at a steady pace. That matches up with C. At time 0, there isn't a height, and then it just grows steady. Number 4, a tomato plant grows quickly at first, so it goes up. Then it remains constant, which is flat. And then it grows at a steady pace, so it goes up. That's going to match up with graph B. And number 5, a tomato plant grows at a slow pace and then grows more rapidly with sun and water. So slow pace and then more rapidly. On the second page, we have two types of graphs. A continuous graph is a solid line, and the solid line is when all those fractions and decimals make sense. And a discrete line is dotted, and this is when there are no decimals or the decimals don't make sense. And we've talked about this, like you can't buy a half a hamburger at McDonald's, or you can't have 2.5 pets. When those halves and fractions don't make sense, that is a discrete graph. And this first one just kind of explains to us what's going on in the graph. Angela's heart rate is being monitored while she exercises. While walking, her heart rate remains the same. She increases her pace, and it increases. She begins to run, it increases faster. Her heart rate remains high while she runs, and then she decreases her pace and her heart rate slows down and returns to normal. And you will notice in the slowdown, it doesn't go all the way to 0. Her heart rate would not be all the way to 0 because then she would be dead. So the heart rate needs to continue. or it needs to be above 0. Number 6, Jenny is selling candy bars to raise money for the school dance. For each candy bar she sells, she gets 50 cents, and she has 15 candy bars that she needs to sell. We might need to extend this graph a little bit because we have to go to 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then going up the side, I'm going to go by 1s, 2, 3, 4, 5, 6, 7, 8. So at 1 candy bar, she gets 50 cents. 2 candy bars, she earns $1. 3 is $1.50. 4 is $2. 5 is $2.50. 6 is $3. 7 is $3.50. 8 is $4. 9 is $4.50. 10 is $5. 11 is $5.50. 12 is $6. 13 is $6.50. 14 is $7. And 15 is $7.50. And I should label the axis. This is how many candy bars she has sold, and this is how much money she has earned. And I'm going to give you a second to get caught up because I probably did that a little bit fast. Number 7, Tim's heart rate is being monitored while he exercises on a treadmill. He jumps on a treadmill and starts running. So that's our first part of the graph. After a few minutes, he has to slow down to a walk. And then after a few minutes, he jogs until he stops. So if he jumps on a treadmill, his heart rate is above 0. And he's going to jump on and start running. So it's probably going to increase. And then once he starts running, it's probably going to be the same for a while. He has to slow down to a walk, so that's going to lower. And then he walks for a few minutes, it's probably going to stay there. And then he feels good enough and he jogs again until he stops. So running, it goes up, and it says he runs for a little bit. He has to walk. You'll notice when he's walking, it's not quite as low as when he started. It comes down, but it's not that low. And then he starts running again, and it stays at that high rate again. Number 8, a pet store is selling puppies for $50 each. It has 8 puppies to sell. So across the bottom, this is how many puppies we have. And I'm going to have up here, I'm going to have this go up by hundreds. There's 100, 200, 300, and 400. So 1 puppy, you earn $50. 2 puppies is 100. 3 puppies is 150. 4 is 200. 5 is 250. 6 is 300. 7 is 350. And 8 is 400. And I don't remember if we were supposed to say this or not, but this is a discrete graph. You can't sell 2.5 puppies or 4 1/3 puppy. Since it's dots, it's discrete. It's a discrete graph. Number 9, we need to write a story for each of these. Time versus the distance from your locker. And you'll notice it's steady here. So I would just say something like, Susie walks away from her locker at a steady pace. So no changes, just a steady pace. Letter B, you go up, and then you stay that same distance away from your locker, and then you get away from your locker much, much, much faster. So I would say something like Susie walks away from her locker. And the second part right here, she stops for some reason. So then I'm going to say she stops to talk to a friend. And then the third thing that happens, she goes away at a much faster pace. That's a much steeper line. And then I'm going to say she hurries to class, so she is not tardy. Letter C, looks like she leaves her locker and then has to come back because the distance gets a little bit away and then it comes back, and then again a fairly rapid rate. So we'll say Susie leaves locker and realizes she forgot her homework. So she goes back. So that's right here, leaves her locker, realizes she forgets her homework and comes back. And number 2, she doesn't want to be late, so she hurries to class. And letter D, excuse me, leave the locker at a really, really fast pace, slow down, and then kind of a constant rate. So for this one, I would say it's Friday, and you are very excited to leave school, so you run away from your locker. At a very rapid pace. And then you get tired, so you slow down a little. Maybe slow down to a jog. And then the third one, it flattens out more. So then you are more tired and you start walking. And the key idea is you leave very quickly and then slow down a little bit and then slow down a little bit more. And these down here are all continuous graphs because you can be 2.5 feet away from your locker, you can be 2.5 seconds away from your locker. And the last page here, I think this is the last page, if you look at this, this is time and this is speed. And this is very, very, very important. This is time versus distance. So right here, this person increases and they're going from 2 miles an hour to 10 miles an hour. So maybe that is when you get on your bike. And your speed increases. And then the second thing here, you remain at 10 miles per hour for a few minutes here. So you remain at 10 miles per hour. And then for some reason you must realize you're running late again. So then this is an increase. You kick it in and you start pedaling faster. You start pedaling faster here at number 3, and then you remain at 25 miles per hour for a while, and I guess I'm just assuming this is miles per hour. So you remain there for a little while, and then number 5, you slow down and stop. Now with the second graph, you'll notice the shape is exactly the same. And here we remained constant at this 10 miles per hour. Here we remain constant at this 25 miles per hour. Well, this graph is going to be similar. Number 1, you went from, let's say, 2 miles to 10 miles away from home, or from 2 miles to 10 miles away from home. So maybe you left your friends and went to another friend's. So you were at your friend's house, which was 2 miles away from your house. You got in a car and you drove there, and now you're 10 miles away from home. This means your distance doesn't change. So that must mean you stayed at your friend's house. So this is where you stayed at your friend's house for a while. And then the 3 of you must have decided to go somewhere else, maybe to the mall. So for number 3, you drove to the mall. And then number 4, this distance doesn't change, so you stayed at the mall for a while. And then number 5, you returned to 0. And we said that in the original part of this question that was your distance from home. And so then you return home. So right here, this means speed remains constant, so you were at 10 miles an hour. And this meant the distance remained constant, so you stayed 10 miles from home.